MEI Statistics Minor chi-squared tests. 1.1 Contingency tables. Now we know that when we're analysing association between two variables, Spearman's coefficient is a lot more versatile than Pearson's, as it requires less strict assumptions. In actual fact, Spearman's coefficient doesn't require assumptions. However, it still requires both variables to be quantitative or numerical. But what if we wanted to investigate for association between a quantitative variable and a qualitative or a categorical variable? What about if both of the variables were qualitative? So example 1, is there an association between GCSE maths grade and A-level maths grade? Well, we know that the new GCSE is quantitative. It consists of the numbers 1 up to 9. But the A-level maths grade is qualitative. It takes values A star down to E. However, A-level maths grades are ordered. So we could assign a numerical scale to them. For instance, a U could be 0, an E 1, and so on. This is now quantitative data. And so we could use Spearman here. However, if we were asked if there is an association between eye colour and hair colour, both sets of data are certainly qualitative. The data is not ordered in any meaningful way, so we wouldn't be able to assign numerical data. So correlation analysis is not feasible here. So when we do have qualitative variables, we use a contingency table. It's a two-way table with one of the variables along the top and one going down the side. These variables inside the table represent frequencies or counts. Note that there is usually some form of other category, and there is always a total column and a total row. If one of those variables is quantitative, it's usually grouped for a contingency table. We still have an other column though. What might that be? Well, it might be for people who got a U grade, or for people who didn't take GCSEs, or possibly for people who did the old GCSEs. Now remember that this approach of grouping data will lose data, but it will probably be necessary for our test. Now, analysis using contingency tables largely revolves around comparing observed values, what the data tells us has occurred in real life, and expected values, what the data should look like if there was no association between the variables. So this first table we've been given is the observed values. It's the data that has been observed in real life. So what would we expect the frequencies to be if there was no association between the variables? Well, the expected values wouldn't all be the same, as for instance there are clearly more people with brown eyes than there are with blue eyes. So what I'm going to do is I'm going to consider this cell here representing people with blue eyes and black hair. So 22 over 126 of the sample has blue eyes. 25 over 126 of the sample has black hair. So if there's no association, and hence the probabilities are independent, we would expect 22 over 126 times 25 over 126 of the sample to have blue eyes and black hair. That is the proportion of the sample we would expect to have blue eyes and black hair. Therefore, in our sample, we would expect that proportion times 126 people with blue eyes and black hair. Now you'll notice that that 126 and that 126 will nice and neatly cancel. So it's simply going to be 22 times 25 over 126, which is 4.37 to 2 decimal places. I'd recommend going to decimal places rather than significant figures here, so that every cell in the table is accurate to the same level. Notice that this formula is the row total, 22, times the column total, 25, divided by the grand total, 126. So to calculate an expected value from a contingency table, use expected value equals the column total times the row total over the grand total. So we can already see that some of them are quite close. For instance, 6 and 5.71, quite close. Other are a bit further out, 12 and 8.52. But are these differences statistically significant? We'll find out in our next video. So the next video is a chi-square test for a contingency table.